Yeah, yeah, yeah.
Okay,
Was
let's
I
get
done?
started. Hi, everyone. Welcome to the Space Science webinar series. Today's speaker is Dr. Luca Montabone. He's from Space Science Institute in Boulder, Colorado, but he's based in France. His area of expertise is the dynamics of dust storms on Mars and their connections with the atmospheric circulation. He has been involved with Martian atmosphere research for about 2 decades now. He has worked on many missions. He has worked with large European Mars projects such as the Mars Climate Database, MCD. He carries out analysis with ESA missions such as the ExoMars Space Gas Orbiter. Currently, he's doing research with multiple satellite observations, planning aerostationary satellite missions to Mars, things like that. He also visited UAE University in Al earlier this year, but he had to go back because of the pandemic. So we couldn't have you physically, so virtually we welcome you
Yes.
to Abu Dhabi. And yeah, welcome to the center, and the stage is yours.
Thank you very much, Dimitra. So yeah, I was in the UAE in January. I spent January and February there, and the plan was to stay until May, and then the pandemic exploded and things went very differently. But I managed in these 2 months to start collaborations, and I'm still collaborating with people the UAE, UAU, particularly the University of the UAE, and specifically on the aerostationary satellite concept that I will give you a few hints at the end of the talk. So this talk is about monitoring dust, in particularly using a variable called column dust optical depth. We are going to see what it is. What I'm going to tell you in this, 45 minutes or so, is something about key Mars facts, just to make sure we are on the same page, that we know a few key concepts during this talk, and then a very short introduction on the dust cycle and dust events, including dust storms. Then we focus more on this variable called column dust optical depth. We're going to see how we can monitor this variable throughout the Martian years. And then the key part of the talk is to show you some of the variability that we can see from this data using past and present observations from satellites. And then we lead into the future by quickly looking at sense satellites and monitor this dust on Mars from vantage points of view and in a new way. So let's start with key facts about Mars. This is a picture comparing Earth and Mars. We see even from this picture that Mars is smaller. You probably had already a few seminars, few webinars about Mars in this series, so I'm not going to go too much into the details, but at least I'll tell you that the radius of Mars is about half the radius of the Earth. The volume is about 15%, so you can put 6.5 Mars into the volume of the Earth. The mass 10-11% of the one we have here on Earth, and the gravity is about 38%. So you would be lighter on Mars. At least you will feel lighter on Mars, but of course your mass will be the same. Now, in terms of the inclination of the axis, we know the Earth has an axis inclination of 23.5 with a 24-hour Mars has a very similar inclination, 25.2, and the length of the day is also very similar, 24 hours, 35 minutes, 35 seconds. So we basically have 40 more minutes on Mars. We can use them to work more or to relax, whatever you prefer. But the important thing is, because of the tilt of the axis, both Earth and Mars have seasons. And this is a plot that shows the 4 seasons on Mars as we have on Earth. The exception being that the orbit of Mars is more eccentric than the orbit of Earth. You see in the panel, if I can actually, let me see if I can show you. There's a pointer, right? So you see here the value of the Martian eccentricity is about 5.5 times the one on Earth. So Mars is more eccentric. The closest approach is in winter, between autumn and winter. And then this is called aphelion, and the aphelion is in autumn summer. Now, the length of the day, because Mars is farther from length of the year, because Mars is farther from the sun than Earth, is about twice the year on Earth. Okay, so if you count your age in Martian year, you would be younger. Of course, not biologically, but just in terms of time keeping. Another concept that is important to of solar longitude, or aerocentric solar longitude. It's an easy concept. It's basically the angle between the position of the sun, the position of Mars at the spring equinox, and the current position of Mars on its orbit. Okay, so this angle, which we call L sub s, is 0 at spring equinox, 90 at the summer solstice, 180 at the autumn equinox, and then 270 at the winter solstice. So this concept is important. I'm going to use it throughout the talk because it's a way to measure the time of the year on Mars, the way scientists use it so far to measure the time of the year on Mars. Okay, there is another 2 interesting concepts to highlight. The first one is that most large dust storms happen in the autumn season and the winter season. Is not by chance. It's because Mars, it's closer to the sun, so it receives more energy from the sun. So that has implications on the strength of the winds. The winds are stronger, and therefore there's more lifting of dust, and there's more there's stronger circulation that can bring this dust at different places at very high altitudes. And the other concept that I want to mention is the concept of Martian year. We have a sort of calendar on Mars. The first Martian year happens to start on the 11th of April 1955. Why this particular date? There's no particular reason to start a first Martian year that day, except that you want to find a date that basically covers all possible observations and then onwards, so that you can refer every event to a specific reference time. And at a certain point, a group of scientists wrote a paper comparing different instruments, and they found that if you go back to at least 1955, you encompass all the important observations made by the Mariner, Viking, and other spacecraft on Mars. So they decided, let's put Martian year 1 at the LS, so aerocentric solar longitude 0, which happens to be on that day. And then from now onward, for that time onwards, scientists and engineers alike used that reference time. So we are still using this calendar. And for according to this calendar, we are now in Martian year 35, which started on 23rd of March last year, 2019. We are towards the end of Martian year 35. Another year that I'm going to mention in this talk is Martian year 34, because this is a year, the last year we had a extreme or global dust storm. Okay, so just remember a few of these years. 35, 34 started in 2017, and then basically every a bit less than 2 years you have a new Martian year. A bit less than two Earth years you have a Martian year. Okay, what about the atmosphere? Earth has an atmosphere. We know that the atmosphere of the Earth is 78% nitrogen, 21% oxygen. Mars has an atmosphere as well. Otherwise, I would not have a job, or I would study something else. The atmosphere is 6% carbon dioxide, and then you have trace gases, which are actually important. And in fact, we have a mission called Trace Gas Orbiter, which is currently looking at these trace gases, because they are traces, but they are important from the thermodynamical and dynamical point of view. In terms of temperature, pressure, and density, the average temperature on Mars is much colder than the average temperature on Earth. We are about minus 63 degrees centigrade. The pressure is much lower. We are 6 millibar compared to 1 bar on Earth at the surface. And the density is lower as well. 0.02 kilogram per cubic meter at the surface. And for Earth, we have 1.22. So want to compare the density of the air at the surface of Mars is about the density you would have on the Earth atmosphere at 35 kilometers altitude. So it's very rarefied atmosphere, and very cold. But there is an atmosphere and there are winds, and this is the reason why we have lifting of dust and storms and meteorological phenomena quite similar to what we observe on our planet. Another characteristic that you can observe from this picture is that the Martian atmosphere layer is red. The reason for this color is the presence of dust particles in the atmosphere. Okay, and this is topic of this talk. Just before going to talk about dust, I want to show you what the topography of Mars looks like, because the topography is also important in terms of interaction with winds and dynamics and atmospheric dynamics, as much as on the Earth. But on Mars, we have topographic features which are even more extreme than Earth, so it's even more important. We have, for example, this Hellas Basin, which is about 5 kilometers deep. We have Olympus Mons, 10 kilometers high. The Taurus Ridge, which is a area, a very elevated area with other 3 volcanoes. Then we have Valles Marineris. These very flat northern plains, which are perfect corridors for dust storms to occur. This Arcadia, Acidalia, and Utopia corridors are actually where we observe most of the dust storms to occur, coming from the northern plains towards the equator and the southern hemisphere. Okay, so let's see what the dust cycle looks like on Mars. Mars is covered in dust. Dust meaning grain sizes of few microns. There is sand as well covering the Martian surface, but for sand sizes, the grain sizes of the sand are larger than the dust. So we talk about like for the sand, only a few microns for the dust. So we are specifically concerned about the dust. It is a cycle in terms of lifting, transport in the atmosphere, and sedimentation back to the ground. So lifting from the ground, transporting the atmosphere, and sedimentation back to the ground. So that's three main mechanisms for which dust particles are lifted from the surface. Dust devil is one. So these are convective vortices. They have a low pressure in the middle, so they can suck dust particles from the ground. Near surface winds is another more important mechanism for which dust is lifted from the ground. But these near surface winds coupled with another phenomenon which is called big sand particles are moved by near surface winds, and they, instead of being lifted, they just, I mean, instead of being put into the atmosphere because they are too big to be put aloft, so they just saltate, so they move around, and by doing this, they kick other particles, and particularly they kick smaller particles, dust particles, so that the dust particles can be lifted into the turbulent planetary boundary layer, where turbulence can act to move it higher in the altitude. Then convective phenomena bring these dust particles and move them even higher in the atmosphere. At that point, the large-scale winds that occur in the mid-atmosphere can trap these particles and move until gravity acts on them, so that they sediment back to the ground little by little. And another phenomena that can occur is specifically related to the presence of water or carbon dioxide ice that can form around these dust particles in the atmosphere. So these dust particles can act as condensation nuclei for the ices. So the ices grow on these dust particles, and this is called scavenging, because the dust particles are scavenged by the formation of ice around them, and then they are taken off the atmosphere, and then of course they, you know, the ice particles sediment they evaporate, and then the dust comes back to the atmosphere. So scavenging is not is an effective way to take some dust particles at different levels, but is not making the dust particles disappear from the atmosphere. So this is the dust cycle. It's a cycle because particles being lifted from the ground come back to the ground after a while. Okay, but by doing this, the dust, the presence of dust in the atmosphere manifests itself with different meteorological phenomena, one of which, probably the most dramatic one, being the dust storms. Okay, so you see in these pictures some
Luca,
of these.
Luca,
Yes.
try switching off your camera. Your audio sometimes gets frozen. So yeah, maybe there is a bandwidth issue.
Okay. Okay. So maybe I'll do that. Let me just stop the video. Okay. So the camera is off right now, is it?
Yeah, go ahead.
Okay. So this, for example, is a very nice example of the dust storm, which is combined with a cyclone. So there is a vortex here, and the storm, the dust is trapped in this vortex. another example of a storm is a front. So again, here we have a meteorological phenomena called front. So it's basically a wave um, of winds that moves, and dust is moving with the front. Another front is showing into this last picture here. Here, this is a combination of a front and the current. So we can visualize the presence of dust in the atmosphere when some meteorological phenomena highlight this presence by showing us nice pictures like this one. Visual images, okay? It doesn't tell us a lot about the amount of dust or how much effect we expect, how much, for example, thermodynamic effect we expect from the presence of this dust in the atmosphere. It does tell us that there is dust, but it doesn't give us any quantitative information. Okay, so that's why we are interested in variables like column dust optical depth, because it gives us some quantitative information. But before getting to this point, let me also show you what how we classify dust events on Mars. We basically classify them in 4 classes. The smallest phenomena are called dust devils. They are few hundred meters size in height, and few tens of meters in horizontal dimension. Then we have local storms with fronts of a few hundred kilometers, going to regional dust storms, which have fronts of few thousand kilometers, up to the very extreme case, which some people call global dust event or global dust storm, planetary encircling dust storm. I like to call them extreme dust event, and we'll show you why. So these are events that basically cover the entire planet in dust, and last for many sols, like a few hundred sols. Okay, you see the difference here when Mars was all the features of Mars were clearly seen, and then a few sols after, the entire mass was covered in dust. This was the last extreme dust event. If you were on Mars at that time, you would see the sun basically disappearing. So this is a picture taken by the rover Opportunity, and you see that at one day when the storm, the extreme dust event, which started in June 2018, wasn't there yet, you could spot the sun very clearly, and then little by little, sol after sol, the sun completely disappeared. You barely see, I'm not sure you can see it from Zoom, but you barely see a dot here, which is the sun. And after this sol Opportunity died, because well, it went into safe mode, because if you have such an amount of dust in the atmosphere, the amount of sunlight that reaches the ground decreases a lot. So the solar panels of this rover couldn't recharge anymore. So it went into safe mode first, and then wasn't able to recover after the dust storm finished. So this tells you also that studying dust storms and predicting dust storms is important on Mars, because if you rely on solar panels, you might have a problem when high opacity like this kicks off. Now, just to put this in context, we have dust storms, as you know better than me, on Earth, sometimes with very high opacity. This is a picture in Dubai, 2015. So even on Earth, in some locations, you reach very high dust opacity, which has also important effect for health and for visibility, of course. You know, air traffic control is a problem when you have such a low visibility. Anyway, how do we get information? How do we get quantitative information from dust? Quantitative information for the dust on Mars? Well, we use satellites and particularly instruments which are sensitive to the infrared radiation. So far, what I did, I used 3 spacecraft from NASA. These are sun-synchronous instruments, therefore they are synchronized with a particular local time. They always observe Mars at a particular local time in their orbit. These instruments were Mars Global Surveyor. Sorry, the spacecraft was Mars Global Surveyor, and the instrument on board was TESS, Mars Odyssey with an instrument called Themis, and Mars Reconnaissance Orbiter, which is still observing Mars as well as Odyssey. So Mars Reconnaissance Orbiter had an instrument called Mars Climate Sounder. So all these instruments, from all these instruments, we can retrieve the column dust optical depth. We can retrieve or we can estimate, depending whether we look at nadir, you know, which is like looking in the vertical direction, or at the limb, which is looking at the slant direction. But let's consider a spacecraft looking at nadir. So the and we look at the picture on the right. The ground emits infrared radiation. So this infrared radiation goes through the atmosphere where there are like dust particles. Some of these absorb the infrared radiation, some others scatter this radiation with single or multiple scattering. At the end, some of the radiation is observed by the satellite in space. The optical depth is basically related to the transmittance of the atmosphere. In other words, the optical depth, which is this tau in this equation, tells us how much radiation is lost between the transmitted flux and the received flux at the top of the atmosphere. And this optical depth is also proportional to the amount of dust which is in the atmosphere. So this equation down here shows that this column optical depth is proportional to the integral in the entire column, in the entire atmospheric column, of the quantity called dust mass mixing ratio. Okay, so in simple terms, if we have an infrared radiation emitted by the ground, the satellite measure how much radiation is transmitted through the atmosphere, and the radiation which is not transmitted is absorbed or scattered, and the optical depth gives a quantitative measurement of this particular radiation. So we have used NASA spacecraft so far. In the future, the plan is also to use non-NASA spacecraft, because other spacecraft like Mars Express, Trace Gaia's orbiter from ESA, and of course the UAE, the Emirates Mars mission, they are not sun-synchronous, so they cover multiple local times. And this is very important in order to have a view of the diurnal variability of dust, which is very difficult to achieve with sun-synchronous spacecraft. In fact, let me show you, I hope the movie shows well. Let me show you what a column dust optical depth from a satellite looks like on the left video, left animation, and we reconstructed maps of a column dust optical depth looks like on the right side. When we observe with a sun-synchronous satellite, we observe this kind of picture, which is very sparse. So we have sparse observations. And the satellite is moving in longitude as well, while it orbits planet Mars. Then we have to reconstruct a latitude longitude map at most locations. So we have adopted a methodology that allows us to do this, but of course it's still a reconstruction. It's not a proper observations. This is the reason why we would like to move beyond the sun-synchronous satellite, because in order to monitor a very dynamical phenomenon like a dust storm on Mars, as you can see in this right-hand side, we need to observe all locations continuously and simultaneously. This is very difficult to achieve with sun-synchronous polar orbit satellites. But anyway, we did our best so far. So we have developed a methodology to grid observations from sun-synchronous satellites. We use an iterative method with successive time windows, 3 sols, 5 sols, and 7 sols. And we calculate averages at a grid point, at grid points, where K in this formula is a grid point. We calculate average of column optical depth by weighting the observations using weights in space, time, and observation quality. This basically means that we accumulate a lot of observations which have different times, and they are in different locations, and they might have a different uncertainties. And we try to come up with one value, one single value, one average value at a particular grid point, which takes into account the weights in space, time, and the quality of the observations. So just to show you how it works, here, for example, you have the observation for a particular Martian year, a particular day from the Mars Reconnaissance Orbiter, Mars Climate Sounder instrument. These are 13 tracks, which means 1 sol of observation. Okay, so the night tracks, you can see them in this particular at these particular longitudes, and the day track, the day tracks are covering the other side of the planet. So we distinguish between night track and day track. The point is that only one track, only 2 tracks per map in longitude latitude map, only 2 tracks have the correct local time of that particular longitude. So this track, for example, is at 3 a.m. and correspond at 3 a.m. at this longitude on the planet, when the Mars Universal Time, which is the time at 0° longitude, is midnight. Okay, and this track here corresponds to 3 p.m. local time when the map is at Mars Universal Time 0. But all the other tracks, they don't have the correct local time at their longitude. Okay, but this is impossible to achieve with a sun-synchronous satellite. Anyway, we can grid these observations by taking into account the difference in time, and we can do for an observational window of 1 sol. We can do for observational window of 3 sols. In this case, you have multiple tracks for multiple days. So we can little by little cover all the holes in the map. We do for 5 sols, we do for 7 sols, and at the end, by using this methodology, we have a almost complete map of column dust optical depth. We can even move the Martian universal time. So instead of having midnight at 0° longitudes, we can move to, for example, 6 a.m. and then 12 noon, and then we can have a column dust optical depth. So this allows to basically obtain a complete monitoring of day by day and even like diurnal time scale of dust optical depth. Now, what do we do with this data? Well, we can use a single day map for anything we want to. Of course, we had to take into account that this is not a fully observed map, is a reconstructed map. So there might be errors or uncertainties in the reconstruction of a single map. The most useful use of these maps is for at least from a scientific point of view, is to study the interannual variability and the seasonal variability of this quantity, the column dust. So this is what we are going to look at now. So here I took zonal mean of every single map and plotted as latitude, solar longitude plots. Every plot being 1 Martian year. Okay, so you have Martian year 24, 25 to Martian year 35, which is the very current one. And indeed, this map, the last map, which has been reconstructed, is about a week ago. So we can get to the very present time. If you look at these multiple multi-annual plots, clearly you see three things. There is the first part of a Martian year. Okay, remember solar longitude is basically a measure of the Martian year, the time in the Martian year. The first half of the Martian year, or at least solar longitude 140, the values of column dust optical depth are very low. Okay, so pink means low dust, blue and then red means high dust loading. So first part of the year, we are far from the sun, the winds are weak, and the amount of dust in the atmosphere is very low. Then we approach the seasons when Mars is closer to the sun, from, let's say, LS 180 onwards, the autumn and winter in the northern hemisphere. And at that time, the winds are stronger, more dust is lifted, dust storms occur, and in fact, this shows up in these plots as high dust loading, so values blue, yellow, and red. Then you notice that there are peaks almost at the same time. There's always a peak around LS240, a secondary peak later on at LS320, and usually there is always a pause in between. Sometimes there are big red patterns which highlight what we call the extreme dust storms or global dust storms. The last three occurred in Martian year 25, which was 2001, Martian year 28, which was 2007, and Martian Year 34, which was 2018. Now, if we summarize all these multi-annual plots into one single multi-annual zonal average, we clearly distinguish this at least this, that, well, the three peaks that I told you, plus another one, the southern high latitude peak. So we have this early peak early in the season around the LS between LS 140 and 180, and then a main peak at LS 220, a late peak at LS 320, and then this southern high latitude peak. Do we understand them? Yes, we do. It would take another talk to proper talk about the dynamics that explains what we see in these plots. But I'm going to give you just a few hints. For example, so the main peak and the secondary peak are linked to some dynamical features occurring on Mars in the winter time. So in winter time, there are waves, baroclinic waves in particular. Baroclinic meaning that they are the intrinsic temperature difference in meridional direction is what creates the instability that originates the wave. So these waves, which are here seen as surface pressure anomaly, have the capacity to generate high winds at the surface in the northern plains. These high winds lift the dust, and indeed, this is one of the region where most of the dust storms originate, the big dust storms originate. Then these storms follow these preferential directions, these kind of corridors or main storm tracks. One coming out of this Acidalia Kreis corridor, one in the Utopia corridor, and one in the Arcadia corridor. So these storms move from the northern hemisphere to the southern hemisphere, where they can expand. And most of them originate these peaks that you see here, the main peak and the late peak. What about in the middle? So as you see from this internal variability, there is always a pause in the middle. So what happens at this time? This has been studied. It's called the solstitial pause. And the explanation is, again, dynamic. So actually, it's a combination of dynamic and thermodynamics. So at this time of the year, CO2 clouds occur in the northern polar region, and these clouds have the thermodynamic effect of these clouds have effect on the dynamics of the waves. So the waves reduce in amplitude, and therefore the effect of the waves, which is lift the dust, is less important. So less dust is lifted and less storms are occurring at this time of the year. Again, this would take another talk to explain in detail this interaction between thermodynamics and dynamics. What about the big patches, the red patches here? These are the extreme dust events. As I said, Martian 25, Martian 27, Martian 34. So if we take a average, for example, focusing on Martian 34, we take an average between minus 60 degrees in latitude and 40 degrees in latitude. We observe the extreme characteristic of this storm compared, for example, to what happened later in the year. Okay, so this is the extreme global dust storms that I showed you in a picture from the ground some slides ago. If we compare to another storm which was just regional later on, you see that the opacity doubled the growth was exponential, and the decay was very long. Okay, so this is the reason why I prefer to call this event extreme, because indeed they are extreme compared to any other storms that can occur on the planet. They are also quite irregular. They don't occur, as we can see from these statistics, they do not occur every year. We might have gap years. We might have two extreme storms after the other. They have a starting time which might be closer to the equinox or closest to the solstice. So these extreme dust events are actually the challenging meteorological phenomena to monitor and forecast on Mars. They are extreme, so they are important, but we are not able yet to forecast them in advance. And one of the reasons is because we don't understand them very clearly. So this particular event actually started as a regional storm, and only at this point in time it evolved into an extreme event because a secondary event occurred. So that's why we call this extreme dust events and not storms, because they are a combination of multiple storms. So I show you a reconstruction of maps in column dust optical depth during this event. And you clearly see this storm started as a plot, and then after a while, even a secondary storm occurred in the left animation, left view. So these are multiple events. They are complicated to monitor unless you have a global view, which can only be provided by multiple satellites. Why not in what we call areostationary orbit? Aerostationary meaning stationary with respect to planet Mars. Okay. Okay. Another interesting aspect of this latest extreme dust event is that first time we observed some diurnal variability. So if you remember this map that I showed you before, these were at different Mars universal time. Here, the local time at 0 degree north, 6 a.m., 12 noon, and 6 p.m. Okay, if you follow, for example, this low column opacity blob, if you follow through time, indeed you see that there is a wave number 1 moving. Okay, and this has been clearly highlighted in time series of column dust optical depth. Maybe we can focus on 3 different locations: Aeonia, Meridiani, and Hellas. Particularly Aeonia has a dramatic diurnal variability. You see from this plot, this is a time series on over 150 sols. This is the value of column dust optical depth. The Aeonia time series is in pink. You see that diurnal variability is very, very large. Okay, and this hasn't been observed before because we were not able, with this sun-synchronous satellites, we were not able to really have a confidence in dayside observations. Now with different retrievals, we can do it, and we see this diurnal variability showing up very, very clearly. Okay. Now, Aeonia Terra is particularly interesting. We did some simulations with a GCM, global climate model, and without any guidance from the dust maps that I showed you, the GCM, when when we plot column dust optical depth anomaly, the GCM shows waves that correspond very much to what I showed you in the observed maps. So here in Ionia Terra, for example, we see the sign of a diurnal wave passing over, which was exactly what I showed you in the reconstructed map from satellite observations. Okay, so we are approaching the end of the talk. Just maybe 2 minutes more to tell you what is the future of atmospheric monitoring for the dust on Mars, and how do we see forecasting of dust storm, for example, happening on Mars sometime in the future. Well, data assimilation is a technique that can certainly help to forecast not only dust storms, but any other meteorological phenomena on Mars. I'm not going into the detail to tell you what data assimilation is, because I know that Dr. Roland Young has given a great talk some time ago, specific about data assimilation on Mars. What I'm going to focus on today is to tell you that not only we need to improve GCMs and data assimilation techniques, but we need to improve the way we monitor dust on Mars. I told you so far we have been using sun-synchronous satellites. EMM is going to change paradigm, because EMM is going to observe Mars full disk continuously, is to move to aerostationary orbit. Aerostationary meaning planet synchronous, equatorial, and circular orbit. Okay, this is the equivalent of a terrestrial geostationary orbit, and it's ideal to monitor rapidly evolving meteorological phenomena like dust storms, because it provides continuous and simultaneous monitoring of the full Martian disk. This is a video, an animation that shows what four aerostationary satellites could observe on Mars. Basically, they can cover the entire longitudes between at least plus or minus 80 degrees latitude all the time, continuously, and they have some overlaps. So you would observe Mars all the time. Concepts like these have been studied recently, involved in a few of them. We started with a concept study for one single aerostationary satellite, which can provide a continuous view of a particular region. But obviously, this doesn't give you a full coverage if you want to look at, for example, evolution of dust storms. Therefore, you need at least 3 of these satellites to cover this lighted area, at least this lighted area, and this light gray area on the surface of Mars. You would be able, with 3, you would be able to observe most of the surface of Mars and follow the meteorology continuously. So this is a concept we call MOLA, monitoring aerostationary constellation for atmosphere and weather in space, because when you have an aerostationary satellite, you can observe towards Mars, looking at meteorology, but you can also observe back to the sun and have a information about the particles emitted by the sun, because the aerostationary satellites most of the time are outside the bow shock of Mars. So we call Macaos because we imagine these aerostationary satellites as nice birds orbiting the planet. And we want to do it for starting or enabling forecasting of dust storms and meteorological phenomena for preparing the human exploration of Mars. And Last but not the least, I've been involved in what we call the ultimate constellation concept, which was a study funded by NASA last year and ending this year, which is called Mosaic. Mosaic is a satellite constellation composed of 5 different types of platforms, including aerostationary platforms. They are in 3 different orbits: aerostationary, polar orbit, and elliptical orbit. And the goal has the ambition to enable the full study of the Mars climate system at multiple spatial and temporal scales. By doing this, we aim to prepare for the future human exploration of the red planet. And with this idea in mind, I thank you very much for your attention. And sorry to have taken a bit too much of your time, but I hope you have at least a few burning questions. And if you have more questions, you can write to me, and I will be very happy to reply to you as soon as possible. Thank you very much.
Thanks a lot, Luca. That was great. Yeah, so the floor is now open for questions.
I sent a couple of questions to you by chat, but you can answer them later. It's not important. Thank you so much for this wonderful talk.
Thanks a lot for inviting me. Sorry it took longer than than I had planned.
It's amazing how much has been done with the data, sparse data that's been available.
Absolutely, and we are looking forward to have much less sparse data from EMM and making much better monitoring of the next years of dust on Mars.
Right. So I'm just curious to know, can you also make use of some of the rover data, such as Curiosity or MSL?
Yes, indeed. Actually, the use we do for this rover data is to validate our satellite maps. There is some discrepancy, actually some important discrepancy between what we observe from orbit and what we observe at the ground. You know, the ground truth might be different from satellite view. So this very precise time series of column opacity observed from ground helps us to check whether the satellite retrievals of column dust optical depth is accurate enough. So yes, we do use them. They are very sparse. They are 3, 4 locations, so we cannot really embed them into the maps. But they are great to validate these maps.
All right. So if there are no more questions, then once again, let us thank Luca.
Thank you very much, and I hope to see you in person sometime in the future after this pandemic is over.
Yeah, after you're able to leave your apartment. Okay, all right. Thank you, everyone. See you next
Thanks
week.
a
Thank
lot.
you.
Okay, bye.
Have a nice afternoon there. Bye bye.
Yeah, thank you.